Okay, so we are wrapping up chapter 13, which is radiation heat transfer. The last few topics in chapter 13, I want to go over 2 examples today and 1 new material. So the new material is what are called radiation shields. Let's take 2 surfaces, very large surfaces, planar surfaces. Left temperature T1, emissivity epsilon 1. The right side temperature T2, emissivity epsilon 2. And of course, we'll assume one is really warm, one is cooler. So let's just say T1 is hot and T2 is cold. They're exchanging radiation heat transfer. Sometimes we want to prevent or at least minimize that heat transfer. One way to do that is to put something we call a radiation shield between the 2 surfaces. So I'm going to show this radiation shield as a dashed line. The radiation shield, I'll show some to you in class in a few weeks when I bring some things in class to show you. But if you want to think what it really is, it's like a piece of aluminum foil from your kitchen. It's very, very thin. It could be aluminized mylar. It has a very low emissivity. So it's like a very thin sheet of kitchen aluminum foil. You put that between those 2 surfaces to cut down the heat transfer from the hot surface to the cold surface. So for this particular model, we're going to assume that, let's put this down here, epsilon shield and the temperature of the shield. Of course, this temperature is going to be different from T1 and T2 because it's in the middle. Now, we're going to assume epsilon 1 equal epsilon 2 equal epsilon shield. We could change that if we want later on, but it makes matters a little simpler if we start out with that. So here's what we've got. We want to find the heat flux from the hot surface 1 to the cold surface 2. So we'll take EB1 minus EB2 divided by the sum of the resistances between those 2 surfaces, T1 and T2. So, surface 1. Space resistance from 1 to the shield. The surface resistance of the shield. The surface resistance of the shield. The space resistance. The surface resistance of surface 2. There's a total, as you can see, of 1, 2, 3, 4, 5, 6 resistances. That adds a lot of resistance to that heat transfer between those 2 surfaces. So the resistance is very large, which means the heat transfer will be much smaller. I'm going to show you on this sketch where those resistances are, just so you know. People normally get confused when you put up 2 of these guys. They say, yeah, but there's only 1 surface. Why are you putting 2 surface resistances? Well, watch the flow of heat from hot to cold. Surface resistance, space resistance, surface resistance, surface resistance, space resistance, surface resistance to T2. There they are, 1, 2, 3, 4, 5, 6. Those are the ones we have there. For instance, if epsilon shield, 0.07. This is from table A8. Far bright. Aluminum foil. So if we put that in there, and of course we're going to let epsilon s equal epsilon 1 equal epsilon 2. If we put those numbers in there, and q double prime, we have to get rid of the area there. So the area comes out of there. Let's get rid of the area. I use double prime there, so we don't need the areas. You can see what F1s and F2s1. Two surfaces very, very close together, infinite in size. The view factor from 1 to the shield is 1, and from 2 to the shield is 1. Put those numbers in there, and you end up with a Q double prime EB1 minus EB2 divided by 27.6. 55.2, pardon me. Okay, now let's contrast that to what would happen if we didn't have the shield there. If no shield. Surface 1, surface 2, no shield, Q equals same thing, numerator, divided by the resistances. Here they are. Surface resistance, space resistance, surface resistance. Right away, you can see what we did. Without a shield being there, there's only 3 resistances. But once we add the shield, we have 6 resistances. So there's a big difference. If you put the numbers in for this, you get Q double prime those 3 resistances add up to be 27.6. Over here, the 6 resistances add up to be 55.2. So you can see the big change. It's a 2-to-1 change. You cut the heat transfer down by a half. So comparing these, Q double prime 1 shield equal 1/2 Q double prime no shields. Our textbook says, in general, Q for N shields equal 1 over N plus 1 Q double prime no shields. So that's it. Now this equation right here is only valid if you let the emissivities be equal. If they're not, you're going to put the numbers in the right places. So there's a qualifier to that equation right there. For space applications, aerospace applications, sometimes they have blankets of shields to protect electronics, sensitive electronics. Sometimes they have 25 to 30 shields, 25 to 30 shields between the hot surface and maybe whatever, the colder surface, which could be facing the sun. Well, you can see how much that cuts it down. If there's 29 shields, then Q double prime with the shields is 1/30th of Q double prime no shields. You cut it down by that factor, 1/30th of the heat transfer with no shields. So, big difference. That's what radiation shields do for you. And what is it? What do? You put a very thin layer of something like aluminum foil or aluminized mylar between a hot surface and a cold surface, and that cuts down the radiation heat transfer dramatically. All right, that's the last official topic in chapter 13. So just so you know, now we're finished with chapter 13. But I'm going to work a couple of examples to show you something else that's interesting in chapter 13. I'm going to, I think I'll put that right here. I'm going to look at a V groove cut into a plate. Okay, so my picture looks like this. The V group depth is 10 centimeters. It's cut in that plate, and this plate is in a room with large surroundings. And the temperature of the room walls, we'll call it T surroundings. Now, surface A1 is both sides of the groove. We call it surface A1. As long as they touch like that, it's okay to call that one surface, not call it, we don't want to call the left-hand side A1, the right-hand side A2. No, because the temperature there of those surfaces are given. So that's T1 and A1. So we know T1, we know A1, we also know epsilon 1. So that's what I know. I've got a V groove, 60-degree angle, cut into a large plate inside a room which is large compared to the V groove. We assume that the V groove is hot, the room is cooler. So we want to find out how much heat goes from the V groove out into the room. All right, so this is a new concept. How many surfaces are there? Okay, there's one, which is A1, and then there's the big room. Now, we've talked, I think maybe, briefly about this with view factors, but here's what we do. We need to construct an enclosure. We want to construct an enclosure. That's important. We construct the enclosure. So what we're going to do is we're going to put a hypothetical surface across the groove. Hypothetical surface across the groove. I think I call that surface 2, yeah. Okay. Now I've made an enclosure with two surfaces, A1, the side walls of the groove, and A2, the hypothetical surface. So I'm going to construct my circuit. We'll assume that T1 is hot and the room is cooler. Okay, this would be EB1, J1, J2, EB2. These are in series, so of course Q1 equal Q2. They're in series. 1 minus epsilon 1 over epsilon 1 A1. 1 minus epsilon 2 over epsilon 2 A2. 1 over A1 F12. Q1, which is equal to Q2, equal EB1 minus EB2 divided by okay, now here's what we assume. We know from back in chapter 12, if we have some small surface in a large enclosure, that the radiation approaching that surface from the large enclosure appears to be black body radiation at the temperature of the walls of the enclosure, T surroundings. So that's what's coming in here from the large surroundings. We model this surface as if it were a black surface. All the radiation leaving surface 1 that goes up this way, it's like it's all absorbed. It all goes in there. It's all absorbed. Over here, radiation leaving this side. When it gets to that dashed line, it looks like it just is all absorbed. If it's all absorbed, that means it's a black surface. So we model that hypothetical surface as if it's a black surface. I'll put a note here. The radiation that comes through that dashed line from the large surroundings appears to have come from a black surface at the temperature of the surroundings. Okay. So I know what he is. I know what he is. My hypothetical surface is a black surface. Epsilon is 1. 1 minus 1 is 0. Okay, so that's what we do. We create a hypothetical surface which gives us an enclosure, and that hypothetical surface behaves as if it were a black surface. I know epsilon 1. I know epsilon 1. Okay, now, obviously, we have to find the view factor F12. All right. Let's get the areas first. Equilateral triangle, 60, 60, 60, 180. Equilateral triangle, all sides are equal. What is one side? Okay. Right triangle, 10. The angle here, 30, 30. I'm going to call that length L, and this length L. Okay, so I've got 11.55 centimeters. My picture right there. Adjacent over hypotenuse. I want the hypotenuse L. Okay. A2 is one side of that, so A2. If you want, you can call it, you can use primes here if you want. It's 11.55 times the depth into the blackboard. We don't know, it's a long groove. A long V groove. Nobody told us how long it was. So if you want to put the primes on it, you can. If you want to put the primes on it, you can. The answer is going to be in watts per meter. Okay, let's take A1. A1 is composed of two sides, left side, right side. A1 prime. 11.55 plus 11.55. 23.1. Okay. Now, let's get the view factors. We need F12. There's an easy way and there's a harder way to get that view factor. Let's take the easier way first. I'm going to use reciprocity. I want him. Look at my picture. F from 2 to 1. Here's A2. Going to 1. F21 is 1. So F12 is equal to A2 over A1. There they are there. 11.55 divided by 23.1. It's a half. Okay, so that goes in here. We know A1, that goes here. We know A1 prime now. We know epsilon 1. We know what this guy is. We're given T surroundings. We're given T1. I think that's all we need. Yeah. Find Q prime 1, for instance. So model it by the resistor network. Do the geometry. Use reciprocity. You got that. Well, you know, if you don't want to do it that way, you can also do it this way. I'm going to change this picture a bit now. I'm going to call this side A1 prime. I'm going to call this side A1 double prime. Now I've got three surfaces. A2, A1 prime, A1 double prime. Here's what I write. The view factor from the combined surface 1 to the surface 2 equal the fraction of energy leaving the left-hand surface that gets to 2 times the area, plus the fraction that leaves the right-hand side that gets to 2 times the area. You have to leave the areas in because the areas are different. They don't cancel out. Leave the areas in. Okay, so let's solve this guy. What's the left-hand side? The length L, 11.55. What's the view factor from the left-hand side to the top? It's an equilateral triangle. F from the left-hand side to the top is 50%, and F from the left-hand side to the right-hand side is 50%. Why? It's an equilateral triangle. It's symmetrical. Okay, 50% plus the right-hand side. The view factor from the right-hand side to the top hypothetical surface is 50%. 50%. Solve F12. A1, 2 times 11.55. Cancel, cancel, cancel. F12 equal 0.5 plus 0.5, 1, divided by 2, 1 divided by 2. It doesn't matter which way you want to work it. There's an easy way and there's a harder way. But they both give you the same answer for F12. They both give you the same answer for F12 here and there. This is much easier, of course. Always look for the easy way out. I didn't solve for number. I just want to show you how you use a hypothetical surface to create an enclosure, and then how you would find the view factor from that right here. Okay, so that's what I wanted to show you there, essentially. All right, now we're going to work the last example that I want to go through in chapter 13. This example comes out of the textbook. It's example 13.4. If you read it in the book, here's 1 page, 2 pages, 3 pages, 4 pages, almost 5 pages. Almost 5 pages, that one example. It's like 4.5 pages. That's a long example. It requires a lot of thought about what's going on. So sometimes, as I mentioned before, I'll work examples in the textbook because I think they might be hard for you to understand yourself reading them at home. So I want to go through this example because it has a lot of interesting things in it. This is the picture . This is surface A1. It's a heater down here. And this is the absorber surface. It's at temperature A2. And T2, let's see what I'm given here. Okay. I'll put that down just a minute. This is in a large room. Whose walls are at T surroundings. Heater, we're providing heat to a heater, whatever, electrically heated plate, whatever it is. This is a absorber. It absorbs some of the heat, but some of the heat is lost out to the room through the sides. Okay. let's put down what we're given here. Okay, first of all, let me give you the geometry. The heater is a plate heater like this, and it goes out from the blackboard like this, okay, like a big rectangle. He tells us what the rectangle is. It's 1 meter here, and I'm going to draw a sketch down here. Here's the heater, 1 meter by 10 meters. It's 10 meters in length into the blackboard. The absorber looks like this. Again, it's 1 meter by 10 meters. So that's the geometry. Okay. So let's go ahead and put down what we know. A1 is known. It's a rectangle, 10 by 1. A2 he tells me that in the problem statement. He says in the problem statement, the area of A2 is 15 square meters, so he's done that for you. A3, I'll come back to this in just a minute. We're going to let that go right now. Epsilon 1, epsilon 2, T1, T2, T surroundings, find Q2. Okay, Q2 up here, the absorber. How much heat is going into the absorber? Okay, it's not an enclosure, okay. The V groove was not an enclosure. So what do we do with the V groove? We made an enclosure. How did we do that? We created a hypothetical surface. Just like in the V groove. That was a 2-surface enclosure. This is going to be a 3-surface enclosure. We now call this surface A3. Just like over here, we call the hypothetical surface A2. Why do we create that hypothetical surface? It gives us an enclosure. The key is this system is in a large room. Over here, that V groove was in large surroundings. So what did the surface behave as? In this example, the surface behaved as if it were a black surface at the temperature of the room walls. Over here. This hypothetical surface behaves as if it's a black surface at the temperature of the room walls, 300 K. So what are we assuming? We're assuming that that's a black surface at 300 K. So the emissivity is 1.0 black. Find Q2, okay. If you want to, we can draw a circuit. EB1, J1, J2, EB2, J3, EB3. Three surface enclosure. Now we're going to put the resistances down. Surface resistances, 1, 2, 3. Space resistances, got it. I'm not going to put all the Q's in. You should do that, but I'm not going to put them all in. I'll put some in. Q1, Q2, Q3. Okay, so I'm going to leave that sit there, and I'm going to do something over here. Okay, what is, oh, I know what R1 is. 1 minus epsilon 1 over epsilon 1A1. Got it. I know R2, I know R3, but this guy is 1 over A1 F12. I need to find the view factors. Okay, so here we go one more time. Step number 1, find the view factors. Okay, 1 to 2. To find F1 to 2. Use figure 13.4. Here's what it looks like. There's figure 13.4. That surface right there, AI, is going to be A1, the bottom surface. See, I can't find F1 to 2 anywhere in the textbook, but I can find F1 to that dashed line. And all the radiation that goes through that dashed line from surface A1, all that radiation that goes through the dashed line from A1 ends up doing what? Striking A2. So I'm going to call this surface right here, it's a hypothetical surface. I'm going to call it A2 prime. Okay, so that's what we do. We put this fictitious or hypothetical surface across here and say all the radiation that comes from A1 that goes through A2 prime ends up hitting A2. Okay, that's why we can say that. So, if I want F12, I got to find F12 prime. Not a problem. That's in figure 13.4. This is 1 meter. This is 10 meters. I didn't put that on there, I don't think. I think the height was 1. Let me just verify that. Let's read the problem again. Oh yeah, 1 meter it is. Okay, this distance from here to here, given in the problem, 1 meter. Okay, 1 meter. Okay, in figure 13.4, we've done it before, we'll do it one more time. X over L, Y over L. I'm gonna call X 1 meter. Okay, L Don't call L a length. It's kind of bad, but don't call L a length. L's a spacing, plate spacing. L's 1 meter. 1. Y is 10. L is 1. 10. From figure, get F1, 2, 0.39. Got it. Okay, from that I can get R12. R12 is 1 over A1 F12. Got it. I'm going to try and get R13. R13, 1 over A1 F13. I need F13. F11 plus F12 plus F13 equal 1. Plane surface, F11 is 0. So F13, 1 minus F12. 1 minus 0.39, 0.61. Got it. Now the hard guy. R23 is 1 over A2, F23. F23. All the rate, the fraction, this is a fraction going from 2 to 3. 2 is a curved surface, out the sides, out the sides. All the radiation leaving surface A2, going out the side walls, shown here. That's the same thing as the radiation leaving A2 prime, going out the side walls. What goes through here ends up here. That's where that came from. That's where that expression came from. So, from symmetry, F2, 3 prime equal F1, 3. F2, 3 prime, this is, they call it 3 prime, I call it A3, 1 to 3. Let me get rid of that right there, F2 to 3. Okay, so that means F2, 3 I replace this F2 prime 3 here. That should be 2 prime 3. I replace that F2 prime 3 with F1, 3 because of symmetry. There it is right there. I've got F1, 3, it's right here, 0.61. I know both these areas. So now I've got all my resistances over here. I've got all my resistances over here. Okay. Now I've got to stop, by the way. What's surface 3? It behaves as if it were a black surface at the temperature of the surroundings. If it's a black surface, what's R3? 0. If R3 is 0, do I know what J3 is? Yeah, we talked about that last time. Yes, I know J3. J3 is not unknown. because the hypothetical surface is being modeled by a black surface. How many unknowns are in that picture now? I know EB1, I know EB2, I know J3, two unknowns, J1 and J2. So guess what I do? I write an equation for node 1. Now I'm going to use equations that we talked about last time. We're not going to solve it any other way. Our goal is to find J1 and J2 by writing two equations. First equation, what comes into node J1 goes out of node J1. What goes out of node J1? Okay. Got it. For node 2, what goes into node 2 equals the current, the thermal current going out. What goes in? EB1 minus EB2 minus J2. What goes out of node 2? What else goes out of node 2? Put a check mark by everything you know. See how many unknowns are left? 2, J1 and J2. Solve those two equations for J1 and J2. Get, when you solve this, okay, here's Q2 right here. Look at this up here. Ask yourself, which is bigger, EB2 or J2? J2, 12,500. EB2, did I get EB2? Oh, I didn't get EB2. Let me put down what EB2 was for you. Let's see here, EB2. EB3, EB2, 7348. Okay, ask yourself, what's bigger, EB2 or J2? 73, J2, oh, J2's bigger, 12,500. 7,400. Okay. J2 is bigger. He's bigger. Okay. So that's why I put J2 first here. J2 is bigger. Here's Q2. So that problem took 4.5 pages in the textbook to go over that example problem. It's very difficult to understand reading it yourself. That's why I spent 20 or 25 minutes in class going over that problem, because there's so many interesting things in there. So many. It's a great way to end chapter 13, because it's so complete in its coverage. How do you find the view factors? How do you model this? It's just loaded with good little things in it. But in the textbook, it's a little harder to follow than what I put on the board here in 3 panels. Okay? So, this ends chapter 13. We are now done with radiation. We're going to be starting convection heat transfer chapter 6 when we meet again.
you.